In the fifth module, we're going to look at fatigue, central and peripheral mechanisms of fatigue, and some of the limits to sports performance. Many of the definitions of fatigue are dependent on the context. We can define fatigue as a reduction in the force or power generating capacity of the muscle, or we could define it as the inability to maintain the required or expected force or power output. And this relates really to task failure. And as you can see from this slide, the required level of force here may be less than the maximum level, and often in athletic events, prolonged exercise or the power output is maintained at a level lower than the maximum, but for a prolonged period. You can see here that over time, the maximal capacity or the maximal force generating capacity reduces, even though the required force may be able to be met. And if we define fatigue with the second definition, then you can see that it takes some time before you get to the point of task failure. However, fatigue is developing continuously, as evidenced by the reduction in the maximal force generating capacity before you get to that point of task failure. So depending on your definition of fatigue really determines how you might examine that. In terms of modifying fatigue, you can do a number of things, and you can see that in this slide. You can change the required level of force. So for example, as you run out of carbohydrate, if you're prepared to accept a reduction in the power output, you can continue on at a lower intensity oxidizing fat. You can also increase the maximal force generating capacity or power of an individual, and that then improves their ability to resist fatigue during a given task. And you can also change the rate of the development of fatigue. That's number 3 here in this slide, and that will determine how long it takes you to get to that point of task failure. It's been debated for many years, where does fatigue reside? Is it in the brain, the central nervous system, or is it in the muscles themselves? The early physiologists in the late 19th century and early 20th century argued that the central nervous system was really where fatigue was. But as you can see from this quote from the text of the English physiologist Bainbridge, he argues that perhaps there's 2 types of fatigue. One with its origins in the central nervous system, and one with its origins within the muscles themselves. And clearly there's interaction between the two, and I'll show you some good evidence of that in a moment. An interesting quote from the famous Finnish distance runner Paavo Nurmi says that he thought the mind was an important part and the muscles were simply the pieces of rubber that kept him going. If we look at the interactions between what's going on in the central nervous system and some of the things that we've examined, muscle, the heart, the lungs, and metabolism during this course, we can see that there are complex interactions between all of these physiological functions. Many things going on in the central nervous system influence our desire, our motivation to exercise, our ability to withstand discomfort and fatigue during exercise. And there'll be changes going on within the peripheral organs, the muscles, the heart, the lungs, and changes in metabolic substrate availability, which will impact on that. And so it's a very complex behavior, is exercise, and fatigue similarly is complex. If we look at just one example of potential effects on the central nervous system, here is the influence of glucose availability on motor drive during a maximal voluntary contraction. You can see that over time, on the left-hand panel, the glucose concentration will fall during prolonged exercise. And when subjects then perform a voluntary contraction and the motor drive is measured as a percent of force, you can see that in the absence of glucose ingestion, that force fell to a much greater extent. When carbohydrate was ingested, there was a higher level of force maintained during that fatiguing contraction. And that's being linked with the effects of glucose availability on motor drive. In many respects, it's a useful safety mechanism to have, that if glucose availability to the brain is declining and the muscles, the active muscles, are consumers of that important glucose reserve, then turning off the muscles is an important mechanism to protect glucose supply to the brain. Of course, if you're trying to maintain your muscle contraction in a competitive environment, then that fatigue is often seen as a negative. And there are a number of examples where various physiological changes can impact on the central nervous system and affect central motor drive and what we call central fatigue. As I've said, the availability of glucose, reductions in oxygen supply, particularly in hypoxic environments. As we saw in the heat module, increases in body core temperature can impact on motor drive. Pain. There's been some recent work that anti-analgesic or analgesic agents blocking pain during exercise can in fact have a slight performance benefit. It's known that drugs that act centrally, such as amphetamines or caffeine, that alter the perception of fatigue, also influence exercise performance. In the case of caffeine, while it has some metabolic effects, these central nervous system effects may in fact be more important in determining exercise performance. And then, of course, experiences, emotions, motivations, a whole range of psychological influences can have a huge impact on the exercise performance and fatigue during prolonged exercise. Professor Tim Noakes and his colleagues at the University of Cape Town in South Africa have proposed the concept of a central governor that integrates a lot of these factors: previous history, training history, current events, feedback from contracting muscles and various other receptors in the body, and coordinate this. And one of the challenges will be to really explore some of the evidence for this, and advances in neuroscience and some of the brain imaging techniques that are now available may shine some light on these complex interactions. An interesting experiment which demonstrates very elegantly the interaction between the active skeletal muscles and the feedback from them and the central motor drive is demonstrated in this experiment, where well-trained cyclists undertook a time trial, and in one situation the feedback from their contracting muscle was blocked through the infusion of anaesthetic into an epidural catheter. And as great care was taken by the investigators to ensure that there was no impact on the higher nervous system, control centres, or on the efferent nerves that went to the muscle that were important for many of the responses to exercise. And the key result here is shown here in this first part of the power curve, which was when the subject's feedback from their muscles was blocked. And you can see when that occurred that they went out at a much higher power output. So in a sense, you could argue that this feedback from the contracting muscles was moderating the central motor drive. When that was eliminated, the subjects went harder. Of course, that came at a cost, and you can see that over time, the power output declined. And part of that is reflected by the increased metabolic stress, the higher capillary blood lactates that we're seeing here. And interestingly, they were still able to have an end spurt as they came to the end of the time trial, but it was less than that in the control trials. But you can see here a very elegant interaction between the central nervous system and the contracting skeletal muscle. Of course, a lot of our attention in this course is focused on the skeletal muscle. And I remind you of this slide, which I showed you in the first module on muscle, the steps involved in the activation of muscle. And not surprisingly, when searching for sites of fatigue or mechanisms of fatigue, particularly as they relate to what's going on in the contracting skeletal muscles themselves, then most attention is focused on those sites and those processes that are involved in activating the skeletal muscle during exercise. So we look at the excitation of the muscle membrane, the transfer of that excitation through the T-tubular system, the release and reuptake of calcium from the sarcoplasmic reticulum, the calcium sensitivity of the myofilaments, and of course the ATP production that maintains those critical processes that are energy dependent in contracting muscle. And in a nice summary here from this review article from David Allen, the University of Sydney and colleagues, you can see that a number of steps in that sequence of events that are involved in the activation of muscle contraction are influenced by various aspects of fatigue. So the excitability of the membrane and the spread of the action potential through the T-tubule system are influenced by changes in potassium and sodium levels, and are moderated somewhat by changes in the chloride conductance. There are effects of various metabolites. You can see here the inorganic phosphate, ADP, reductions in ATP, and increases in reactive oxygen species, which can impact on both SR calcium release, but also on SR calcium uptake, which in turn will influence the available pool of calcium. One observation that's been made is that increases in inorganic phosphate find their way into the sarcoplasmic reticulum and can precipitate with calcium. Of course, the actin filaments themselves are influenced. There are changes in calcium sensitivity and direct effects of inorganic phosphate and ADP, for example, on the mechanical aspects of cross-bridge interaction and force generation. Just to give you a few experimental examples where some of these processes have been implicated in fatigue. And here's a series of elegant studies in isolated single fibers from mice, because they're small and can be easily loaded with some of the fluorescent indicators that are used to monitor the calcium levels. You can see when this mouse muscle is stimulated, initially at a certain rate and then at an increasingly higher frequency, the force production goes down, and you can see that towards the end of this fatigue run, you can see that the calcium level, measured in this case with one of those fluorescent dyes, is much less. And if you apply caffeine to this preparation, we know that caffeine will stimulate the release of calcium release channels. You can see that increasing the calcium release is associated with an increase in force. And so this has been interpreted that reductions in calcium release are critical at this point of fatigue. My research interests over the years have been on muscle metabolism, and so my bias perhaps has been around energy metabolism. There are some interesting questions that one could ask. Here is an experiment done in isolated human muscle that was electrically stimulated and with circulatory occlusion. So it's effectively an anaerobic exercise model. And you can see over time, with contraction, the marked drop in force, which reflects the fatigue that's occurring. And the ATP turnover that you may recall from our lectures on fuels, the relative contribution of phosphocreatine and anaerobic glycolysis. And you can see that over time, this decreases. And there's a very close relationship between the reduction in force and the reduction in ATP turnover rate. Now, I could suggest to you that this reduction in force is a direct consequence of the reduction in ATP turnover. Alternatively, you might conclude that with a reduction in force, there's less requirement for ATP, and therefore the ATP turnover rate declines consistent with that. And that's an interesting question to debate or to ponder when you think about what might be causing fatigue. The availability of muscle ATP is important, and one of the processes that's dependent on ATP is calcium release. And you can see here that the release of calcium in response to a depolarization is influenced by the concentration of ATP. And because ATP is also bound with magnesium, and when ATP is broken down, that magnesium is released, you can see that for a given magnesium, or as you increase the magnesium concentration for a given ATP, that calcium release is reduced. Now, these levels of ATP are very low, and at a whole muscle level, we don't often see them at that level. It's very difficult to measure. But at critical points within the muscle, critical locations within the muscle, it's possible that the ATP concentration could be critically low and affect some of these important cellular processes. And one of the fuels that provides ATP is glycogen. And as we'll see in one of the later lectures, muscle glycogen is very important, and its availability is important for metabolism during prolonged exercise, and running out of glycogen is associated with fatigue. And often, at fatigue, reasonably modest levels of glycogen are being observed. But as this electron micrograph shows, it might be the location of that glycogen which is just as important as the absolute amount. And you can see that there is glycogen here with these black dots within the myofibrillar space, but also you can see between the myofibrils at key points where here's the SR and the T-tubule, and this glycogen might be important in fueling some of those energy-dependent processes that maintain the excitability of the muscle and the calcium release. And finally, in this introductory lecture, how do we try and enhance fatigue resistance? Percy Cerruti was a distance running coach in Australia, perhaps most famously known for being the coach of Herb Elliott, who won the 1500-metre gold medal at the 1960 Rome Olympics. He was a highly accomplished middle distance runner. You can see from his quote here that trained athletes are men immunised against fatigue. They must resist pain and exhaustion. And certainly the ability to resist fatigue is important in the performance context. I'd remind you, however, though, that fatigue may have an important role in protecting the organism from a greater danger. And often there is a fine line between glory and catastrophe in elite sporting events, and we need to bear that in mind. But from a competitive perspective, increasing fatigue resistance is an important way of increasing competitiveness in these sporting events. The way that that's done is by training, and that training might be physical training, might involve technical training in those sports that have a very high technical component. And of course, mental training, as we spoke about the central nervous system, the experiences, the emotions, getting used to certain situations, and training provides those experiences. Nutrition, with the focus on carbohydrate and fluid, as we've seen, and protein nutrition increasingly has been shown to be important, certainly in terms of maintaining and perhaps building muscle mass. In the heat, acclimatization and cooling are important. And then perhaps when all of these things have been optimized, maybe even maximized, the will to succeed often leads to investigation of some of those other techniques that might be used. Supplements, drugs, and gene doping. And of course, lots of publicity recently about the use of some of these strategies to try and improve performance. And great efforts on the part of the regulatory authorities to try and track down that and to minimize that use. And of course, that's one of the great challenges that sport has to confront.